Good. So yeah, DisCoPy. The name stands for Distributional Compositional Python. So you just take DiscoCat and replace the cat by Python. So it started as an implementation of DiscoCat, and it turned into more generally a toolbox for quantum computing, for computational linguistics, and for applied category theory. So let's have a brief outline for this talk. First, I'll talk about diagrams. Diagrams as a data structure for quantum and for linguistics. And then functors as a way to do high-level and high-performance computing. And finally, a few words on diagrammatic differentiation and its application to Qnlp. So the references that this talk is based on, first, the DiscoPy paper that we submitted to Applied Category Theory 2 years ago with Giovanni and Bob. Then a little abstract that we submitted to QPL just this year with joint work with Richie and Giovanni again. And also my PhD thesis, which I defended last Friday, and which will, thank you. And which will appear sometime soon once I have done the corrections. So let's get on with the talk. A little bit of maths just to warm up. So a monoidal signature is a tuple. It's got a set of wires, sigma 0, a set of boxes, sigma 1, and then it's got these two functions that map every box to the list of input wires and output wires. So here the little star will be the Qnlp star, so the free monoid, the lists of wires. Now a triple, a layer is given by a triple. It's got some objects on the left, a box in the middle, and some objects on the right. So let's look at what DiscoPy, how DiscoPy implements layers. Well, you can implement tie will be the sigma 0 in our case, so the types for the wires. Box will be sigma 1, and ID is just some bureaucracy that we need to keep the types in check. So you start with some types, x, y, z, w. A box, F, will have some domain, y, and some codomain, w, so the input and output wires. And then you put it next to an x on the left and a z on the right, and you get a little layer. So you can draw this layer, but you can also store it as a piece of Python. So what can you do with layers? Well, you can compose them in sequence, and you get diagrams. So a diagram will be given by a domain, and then a list of composable layers. So just give me D1 up to Dn. Each is a layer, and each composes with the previous. So the domain of Di plus 1 is the codomain of Di, and also it type checks with the domain of the diagram overall. So for example, the identity diagram has no boxes in it, so it's just got a domain, and it has no layers at all. So that would be the empty list. Now, once you have diagrams, you can compose them in sequence, just concatenate the lists, and you can compose them in parallel, which means that essentially you do first the left guy with some wires on the right, then you do the right guy with some wires on the left. So sequence, composing in sequence is this double chevron here, and composing in parallel will be this little @ symbol. That's the closest we could find in Python. So let's draw a little diagram. We'll need more boxes if we want it to be interesting. So let's have some G, H, E. They all have domains and codomains. If you don't want a codomain, well, you can always have this tie open close bracket will just be the empty list of wires. And now let's compose some things together. So G, then the layer that we've just defined before, then E next to H, and you can draw the thing, and it looks like this. So we have our box G first. It's got three wires out. Then you do F in the middle. Then you do E on the side, and H. Well, you get a diagram. And I guess the point is you can draw this diagram, but more importantly, you can store it as a piece of Python. So that's good. So sometimes two diagrams will represent the same process as Duško just mentioned. And DiscoPy allows you to do diagram rewriting so that you can first check if two diagrams are equal up to your notion of equality, or you can also use it to find an optimal diagram for a given process. So as you just noticed, well, these two diagrams will be equal in the sense that here the box E and F are independent. There are no wires in between them. So it doesn't matter whether I first do E on the left and then F on the right, or vice versa. And that's called the interchanger. So here I have my diagram that I've defined before. I have the normal form of the diagram on the right. And if you call diagram.normal form, you will get the guy on the right. So that's a way of checking if two diagrams represent the same process. You can also use it to do optimization. So now we can add more kinds of boxes. So we can add special boxes for swapping two wires. We can add boxes for cups and caps that we've seen a lot today, for spiders. Basically, any kind of diagram that you can find in Bob's book, you can draw it in Python now. So, well, one application for these diagrams is linguistics. So the idea is you can represent any kind of grammatical framework in terms of diagrams. So here's a little example with a context-free grammar. You've got a bunch of vocabulary, Alice loves Bob, a bunch of non-terminals, S, N, transitive verb, intransitive verb, and then you've got a bunch of rewrite rules. So that would be a context-free grammar. You have the rule that tells you that Alice is a noun, the rule that tells you that if you have an intransitive, if you have a transitive verb next to a noun, you get an intransitive verb phrase. If you have a noun next to an intransitive verb phrase, you get a sentence. So that's a little grammar. And a derivation, a grammatical derivation in this grammar will correspond to a diagram. So here our diagram will be a tree because we have a context-free grammar. Yep, go ahead. Well, I don't encode anything. I guess the linguists would encode stuff. And I guess that's a matter of linguistics in the sense that you will define a grammar, and your grammar will depend on the language you're trying to describe, but will also depend on the level of precision you want in your grammatical model. So I guess here the idea is you have all the freedom you want. You can come up with any kind of rule. Here I just picked sort of a stupid example, or the simplest example I could pick. But if you wanted more complicated examples, you could. Here, basically, the example is a context-free grammar. So by definition, a context-free grammar has a vocabulary, a set of non-terminals, and a set of rewrite rules. And it also has this property that the rewrite rules always have exactly one guy on the right-hand side or left-hand side, depending on your convention. So essentially, any context-free grammar gives you a bunch of these rules. The rules, they are boxes in DisCoPy. So now, if you have a bunch of these boxes, a bunch of these rules, you can compose them. And here it happens to be composed in the shape of a tree. So this tree would have the sentence type as a root and the terminals as the leaves. And now this diagram you can think of as a proof that Alice loves Bob is a grammatical sentence in this particular grammar. So if you come up with more complicated grammars, you can describe more complicated languages. So I guess if you had a context-sensitive grammar, for example, now your rules would take context into account in the sense that you wouldn't have this property of only one output to each rule. But that's a little example of a context-free grammar. We can play the same game with pre-group grammars, which are the ones that Bob has been using a lot. So I guess that was the minimum we wanted to do with DisCoPy was to draw these pre-group diagrams. And here's what it looks like. You have a sentence type and a noun type. Now you have some nouns, Alice and Bob, a verb, loves, that has this complex type like the right adjoint of N on the left, the left adjoint of N on the right, and the sentence in the middle. And basically what that tells you is you can take Alice loves Bob, cancel the N with its adjoint, and similarly on the other side, you get a grammatical derivation. And this diagram is a proof that Alice loves Bob is grammatical in your pre-group. Yep. So I guess in the context-free grammar case, what this would look like is you would have rules. Here you have the rule Alice goes to N, but maybe Alice could be a verb. I don't know. It could be any other thing if you invent your own language. and you would have potentially many rules that correspond to the same word. So for example, the word type is both a noun but also a verb, and in this particular framework, you would model this as by saying that I have two rules, a rule that takes type to noun, a rule that takes type to verb. And so that's how you would model lexical ambiguity, in the sense that if a word has several types, it comes with several rules that sends that word to the different types. And in the pre-group case, the way you would say this is that you define a pre-group as a bunch of dictionary entries, and the same word could have many dictionary entries. So if type is a noun, it has a dictionary entry for that. If it's a verb, it has another dictionary entry. And those would correspond to different boxes in DisCoPy. So I guess that's the main takeaway here. Word is just a kind of box, which was sort of suited for pre-groups, but it's just like any other box. And if you give me a collection of boxes, essentially what you've defined is a grammar. So, well, I guess you also need to tell me what your sentence type is. But all right, so that's a pre-group grammar. You can do context-free grammar. You can do any formal grammar, like context-sensitive or even unrestricted grammar, if you like. We've worked with dependency grammars, and I guess, yeah, modeling more grammatical frameworks is future work. So you can use diagrams for grammar, for formal linguistics. You can use diagrams for quantum computing. So any kind of quantum process you can draw as a diagram. And so here's a little example with a circuit. Well, from DisCoPy.quantum, you import the control knot, you import the Hadamard, the X rotation, the ket, and then square root even if you want some scalars around. And you can compose those together to make a circuit. So here we have a ket with 0, 0, followed by an H on one qubit and a X rotation on the other. Then we do a control knot, and ta-da, you get a diagram. So that's the diagram for a circuit. You can also draw diagrams for the ZX calculus that Bob came up with and Ross. So you take your circuit and you can replace the gates. So this controlled NOT gate, for example, you replace it by a green and a red spider. And now you can map your circuit to the ZX calculus using DisCoPy. You have this circuit to ZX method. And you can also use DisCoPy to call other dedicated libraries for rewriting diagrams in the ZX calculus. So for example, if you took this diagram here, it's got some complicated stuff like a Hadamard gate, but if you simplify it, you get a very simple diagram on the right. So that's sort of the main feature of DisCoPy is it allows you to draw any kind of diagram and then to map from one kind of diagram to another, and potentially use these diagrams as a high-level way to represent computation, so that here you can rewrite your ZX diagram and it would correspond to optimizing your quantum circuit. That's the general idea. And we keep on adding more tools to the toolbox. So on the quantum side of things, we've been implementing classical quantum processes. So basically all of Bob's Dodo book now is implemented in Python. So if you take any piece of his book, you write down the diagram in DisCoPy, and you can start playing around with any classical quantum process. So essentially that means you need extra kinds of wires for the classical wires, and that way you get more processes that you can talk about. You can do, so from qubits, which is the example I'm showing here, you can go to arbitrary dimensional qubits, which are for now not very useful because the quantum computers we have access to right now don't use anything else than qubits, but well, people work with qtrits or whatever, so you can implement them in DisCoPy. We've been working on symbolic circuits, so circuits come with parameters, like the X rotation here is parameterized by a phase, where you can put a symbolic parameter inside. So we'll get to see a little example of that at the end of the talk. And we've been doing more work on a different paradigm for quantum computing, where instead of qubits and gates, you have quantum linear optical computing. So you have photons and you have interferometers between them, and you can do quantum computing with this. And that's still work in progress based on some theoretical work by Giovanni and Bob. So we're implementing that. And now, OK, we have diagrams. Diagrams are very general. They can represent cooking recipes. They can represent grammatical reductions. They can represent quantum processes. What do we do with these diagrams? Well, functors take a diagram and interpret them. So what is a functor? It's got an object mapping. It sends types to types. An arrow mapping. It sends boxes to diagrams. So one example would be circuit to ZX, as we've just seen before. Another example would be qubit to photonics. That's what we're working on. And the main example, I guess, the topic of this conference is Qnlp models. And these Qnlp models are functors as well. So you take your grammatical sentence for Alice loves Bob, and you send the verb loves to some ansatz. You send Alice to ket 0 and Bob to ket 1. You apply the functor, and you get a little circuit. So this was basically copied and pasted from 3 years ago, the first Qnlp conference. And basically, that's what DisCoPy was implemented for, to run these Qnlp experiments. Now, we have different ways of evaluating these functors. We can execute them on quantum devices using the ticket compiler. We can also do high-performance classical simulation using JAX or PyTorch, TensorFlow, TensorNet, or any kind of backend you want for evaluating diagrams in terms of matrices. So last bit of the talk, well, we have functors for Qnlp. They come with parameters, and we'd like to find the optimal parameters in some task. And well, we need gradients. So well, with Richie and Giovanni, came up with this diagrammatic differentiation where you can differentiate any diagram, and it obeys very simple rules like the product rule for composition and for tensor. And you can differentiate ZX diagrams, so here's the differentiation for spider. And well, you can also differentiate circuits that are evaluated as quantum processes by using the parameter shift rule that comes from this Schuld et al. Result. So essentially, use the quantum computer to compute its own gradient by shifting some parameters. And here's what it looks like in ZX. You have some gate and its conjugate. You tensor them together. You take the gradient of this, and you can rewrite it as a sum of, or a difference of the same diagram shifted by some pi/2 phase. Some notes, we don't need to care. OK, how does it look like in DisCoPy? Well, first you import some symbol from SymPy. You put it as the phase of your, as the parameter of your circuit. And now you just need to do circuit.grad, and you get a sum of circuits that evaluate to the gradient of the original one. And basically, you can use this to find the optimal functor in your Qnlp task based on some data. So that's it. What's left as future work? Well, we want to do more linguistics. So for example, Mernouche talked about anaphora and ellipsis earlier today. Using Fock spaces, we want to implement more of this in DisCoPy. We want to do more quantum stuff. So photonics also happens to be about Fock spaces, and that's work in progress. And more applied category theory in general. So there's been work on using DisCoPy to do cognitive science, and well, I hope there will be more. So please get in touch and contribute to DisCoPy. It's open source, and we're always looking for more contributors. Thanks.